then I was an instructor for 15 years over at Cuyahoga Valley Career Center, and sort of retired from that and got into software development. And along the way, I was working for a company called Thermal Engineering. I don't know if you guys remember the old thermal vacuum gauge company, but I was working for the company that actually made that old analog thermal vacuum gauge. And I happened to run across a book called The Meeting Has Been Recorded. Okay, got it. I happened to run across the book back there. Let me see if it's going to let me do my stuff now. I just got to click it, I think. Yep, it was called The Vacuum for Service Engineers. And I don't know if you know Dan Houlihan, but one of the things he always talked about was the dead men in this industry. And these guys were from this book was written in 1959. These guys are long since gone. And this book was like a piece of marketing material back when marketing was actually education. And they would teach people about vacuum and all the things. And so I sat down, the guy gave me a copy of this, and I sat down and started to read it. And it was like reading the King James version of the Bible. You know, it's like, holy cow. You had to sort of get to understand what they're trying to tell you. And there's a lot of information in there. It just made it sort of a challenge to understand at first, but weeded through it. I ended up actually buying the copyright to the book and rewriting it, but not rewriting it, be like rewriting the Bible. So I actually reprinted the whole book the way it was, redid all the illustrations in the book, redid all the math in the book, and then added an addendum to the back that brought it up to modern day stuff. But there's so much in there. So we're going to go over a little bit tonight. And I got a demo. I want to show you guys some stuff about vacuum and hoses and things like that as we go. So the first thing we're talking about is vacuum pumps don't suck, right? And pressure always flows from high to low. That's a really important concept to understand. Like, we're going to cover some fundamentals. Everybody goes, oh, I know the fundamentals. And it's like, we think we know the fundamentals, but I don't think you can know the fundamentals enough, because if you really think about it like a vacuum, everybody thinks about vacuum and sucking. Well, vacuum creates an area of low pressure, but the pressure, the atmospheric pressure, is pushing into the vacuum pump. Its pressure only flows one direction, from high to low. So atmospheric pressure is pushing in. When you're on your vacuum cleaner, you're vacuuming the floor, the atmospheric pressure is pushing the dirt into the vacuum cleaner. It's not sucking in. Pressure only flows one direction, high to low, right? And the pressure gets pushed in the vacuum cleaner, the pressure gets pushed in your pump. When the pressure becomes too low, eventually the flow stops, right? So there's a point where if you were to take a glass Coke bottle and you were to suck on that Coke bottle, you initially get a little suction in there, but eventually you can't pull any harder on there. The flow stops because it's just built up to your lung pressure. It's the same thing with that vacuum pump. Phil, when he came in, he goes 29.92, 14.6, 14.696. Yep. And that is the deepest vacuum we can go, or 0 microns, right? And at that point, flow stops. We're talking about vacuum. I think so. You know, it's interesting to think about atmospheric pressure, right? Because the sun hits the earth warms up, creates gases, and those gases push from high to low. So we're actually pushing. Again, pressure only goes one direction, high to low. That's why pressure at sea level is higher than it is at altitude, because the earth is getting heated, the gases are getting pushed. And so the higher up we go in our atmosphere, the lower the pressure gets. At about 56 miles up, 300,000 feet, we're at 0 psi. We're basically an empty space of vacuum. As we get closer to sea level, we're at 0.696 psia, and about half the total atmosphere is at 3.75 miles up. A quarter of the way to the atmosphere is at 7 miles up. So that's about where we fly at, and it's just showing you where, sort of where the clouds lay on there. But our atmospheric pressure is just generated from the sun heating the earth. When we talk about vacuum is just any pressure lower than atmospheric pressure. Nature creates a higher vacuum than we can ever attain by man. No matter what we do on Earth, we can never achieve a perfect vacuum. And the vacuum that we work with in our HVAC industry is called a roughing vacuum. If you're working in the vacuum tube industry or in space industry, where we stop is where they start. In fact, our pumps pull down to about 25 microns. that's still considered a roughing vacuum in the deep vacuum industry. They go down to 10 to the -6 torrs. They're going down far, far below 1 micron of pressure. A high state of vacuum is also that of a low state of absolute pressure, right? The deepest vacuum we contain, we talked about that already. In practice, we can only get a partial vacuum. And what we're trying to do is get out the free air and the moisture. That's really what it is. It's dehydration and degassing. Degassing happens first. Then after that's dehydration. And about when we're down at under 1,000 microns, about 99% of the load is moisture, right? At that point, we're just pulling moisture out of the system. All the air is pretty well gone at that point. It's just moisture in the system. Now, gas is this is an interesting concept to understand. We have 100 cubic foot of gas and we exhausted it at a rate of 10 cubic feet per minute. There still remains 100 cubic foot of gas in the tank, whether we evacuate for 10 hours, 10 minutes, or 10 years. Okay, it's still going to have the same amount of volume of gas in that tank. Now it's at a lower density. It's at a lower density, but it's still whatever gas is occupying that container is occupying the full volume of that container. All right, so there's fewer molecules, so the tank has a lower, so the tank pressure is lowered in direct proportion to molecules removed, but the remaining molecules occupy the entire space, right? So the volume of the tank never changes. So when that pump, when we're pumping, that's an 8 CFM pump. It's always displacing 8 CFM. It's always displacing 8 CFM. But the flow goes down to the pump. When you fill the exhaust, we get lower and lower flow. That's mass flow rate versus volumetric displacement. Okay. Vacuum is a really poor conductor of heat, and this is actually how a vacuum gauge works. I have this one here is an AccuTools Blue Vac, and what you're looking at is the circuit board. That little circuit board, if you look in the end of this vacuum gauge, that little circuit board's in the end of this right here. And so that is in the end of this opening, and then there's inside there's a thermistor that's about the size of a grain of sand. That thermistor gets up to about 800 degrees. So when we're turning on this gauge, the thermistor kicks out about 800 degrees Fahrenheit, heats up instantaneously, and then all the air that's around this thermistor conducts heat away from the thermistor to the edge of the gauge. And so what it does is we can measure the current. So once this gets up to temperature, we know how much current it takes. And then basically, as we draw a vacuum on it, the heat does not conduct away as quickly, and then the thermistor requires less and less current to run. So when a vacuum gauge is powered on an atmospheric pressure, it uses a lot of current. Once it's up and running in a vacuum, the deeper the vacuum gets, the less current it consumes, right? So, and it's basically gases under deep vacuum are poor conductor of heat. As the molecules are removed, there's fewer and fewer left to bump each other and transfer the heat. And this is why we use vacuum for things like a thermos, right? The conduction, convection are blocked by the vacuum. Radiation is blocked by reflection. Vacuum sensors work with this exact same principle. So how does a pump pump? Well, gases in a vacuum are always seeking equilibrium, and the vacuum pump acts like a trap. So the gas molecules flow into the pump, right? So if we start this pump up here, what's going to happen is going to take a second because it's just going to do that. The pump creates an area of low pressure right here. So as it sweeps away, it creates an area of low pressure, and the atmospheric pressure pushes into the pump. Exhaust out, and then we have a valve here so it can't go backwards on here. Now they're going to introduce a gas ballast here in just a minute here on this. And a gas ballast, basically, what we said before, how much of the load is moisture here? When I get into a deep vacuum, maybe a further slide up. So it probably is. So when we interject the ballast, then I think I'll hit it another slide here. All right. The hose is simply an extension of the vacuum of the vessel being evacuated. So when we have a vessel here and we have a hose, it's simply, again, we're always pushing out of the vessel into the pump. So if we're talking an air conditioner, we're evacuating an air conditioner, the pressure is pushing out into the pump. So think about that for just a minute. If you go grab a straw, like if you got a coffee stir and you blow through a coffee stir, really hard to blow through a coffee stir. If you get a big straw from Sonic, you can blow right through that sucker, right? So the larger the diameter of the hose that we're have on the end of that vessel plays a huge factor in how fast things evacuate. In fact, the pump is the smaller factor in anything. We'll cover that, and this is where the law of start comes in. So this book, 1959, right? There's a couple things here that are real important to realize. So it's important to realize the conductance speed of a line. It means how fast the flow is through a line. Is not increased merely by its inside diameter, but the mathematical ratio of the diameter raised to the third or the fourth power. So when we go up one diameter in hose size, we're going up 3 to 4 times in flow, right? The conductance speed of 1/4 inch tubing is too small to be used as a connecting line to the system, so we'll not even discuss it. Never use it if you can avoid it, as it's too costly and excessive pump downtime. 1959. You know what everybody uses to evacuate systems? Right here, manifold gauge set, right? 10 foot, and you think about this for just a minute, these hoses don't look that long, but there's 10 linear foot of hose right here, plus the manifold connecting, it's 60-inch hoses. So I got, if I'm hooking up to my vacuum pump, I got 5 foot of hose on the yellow, 5 foot of hose on the blue. I got 10 foot of hose, and the number's gonna be important here in just a minute as we go through this. Effective undersized lines. Whenever we know this, main reason for explaining the line sizing is to show the handicap undersized line of the undersized lines and greatly reducing the pumping capacity of high vacuum pumps, right? So a conductance speed bigger is better. And I actually wanted to show you guys this because I think it's just an interesting demonstration on here. So what I have here is I brought some hoses and I brought a vacuum gauge. This is a Dwyer flow meter on here. And so when I turn this pump on here, let me open up the 1/2-inch port here for just a minute. We'll just make sure it's calibrated. It's a DC pump, so it starts up slowly. All right. So that right there is 1.5 CFM. That's what the pump is flowing on that port. Now, as soon as I block this port off here, obviously it's going to go back down to 0. Little delay there on my pump. It'll go back up to full flow again. All right. I'm going to cap this off. And I'm going to put on just the 1/4 inch port for a minute. We'll just see what the 1/4 inch port will do. So full flow with a 1/2 inch port on there. We just went to a 1/4 inch port. We're at about, about 5.5 CFM, right below 6 CFM of flow. So this 8 CFM pump is not designed to run on this 1/4 inch port. Now, if we go to the 3/8 port, we should go back to full flow again. So we're just a hair under, but pretty close. So let's see what happens here for a minute when we hook up to a 1/4 inch hose. I want to show you a couple different things here because they're important to do. So I'm going to open up just one side of the system. It won't matter whether they open up one side or both sides. And I'll show you a couple things I want to show you right away. They're important to grasp here. All right. So, even. That's it right there. We're at. Okay. Now we just reduced the 8 CFM pump to 0.5 CFM of flow. 0.5. Right. So no matter, here's what I want you to understand. If I put a 12 CFM pump on here, a 15 CFM pump, the most flow that we could ever attain is 0.5 CFM through these hoses and gauges here. Doesn't matter whether I open up both hoses on here or one. This is about 0.5 to 0.7 CFM of flow. Everybody thinks, oh, I'm just going to go ahead and get a bigger vacuum pump, and I'm going to get a bigger vacuum pump, and it's going to do more work. Well, what's the limitation on pressure is what? What's the most pressure we can draw? Negative. What? 14.7. No matter how big of a pump we get, we can only pull negative 14.7. So, we go to the Appion Tez 8 hose. And this is a 1/4 by 3/8 hose. I'm going to hook up the 3/8 end here to the pump. I'm gonna cap the quarter in. And we are at about a little bit less than 6, about 5 CFM of flow on this hose, right? So again, with this hose here, with 2 of these hoses, I could get up to over the CFM of the pump. Let's go back here. I'll show you an interesting one. Now this is a 3/8 by quarter. Oops, half the quarter. Otherwise, I have a 1/2 inch end on it. All right, so now this is obviously we're back up to 8.5 CFM. Now, let me shut this off for just a minute. So we have 3 different hose sizes here. We just showed a quarter by quarter, 3/8 by quarter, and this is a 1/2 by quarter. They're all 1/4 inch ends, but all of them had different flows. So what's that tell you about the opening of the hose, the end of the hose? Why does this quarter? Everybody always talks about, well, what does it matter? I have 1/4 inch ports on my unit. What does it matter if I have? Why would it matter if I change hose size if I got 1/4 inch ports? What can you tell me about the 1/4 inch port on this? That's different than the 1/4 inch hose.
That's only one little tiny bit versus the big.
That's right. Yeah. Yeah, that's exactly right. We're talking about when we get into this here, what we're talking about is a couple different things. So just to put this in perspective, 10 feet of hose, 10 feet of 1/4 inch hose at 1,000 microns has a conductance speed of 0.5 CFM. 10 feet of 3/8, 1.5, 10 foot of 4 foot, 10 foot of 1/2 inch hose is 4 CFM. This hose is a 6 foot. That's why we had a little bit more than, we had like 5 CFM of flow, 5.5, I think. 10 foot of 3/4 hose is 1,000 microns, has 16 CFM of flow, double what that pump has. 3 foot of 3/4 inch hose, which is what I tested here, has a conductance speed of 56 microns or 56 CFM. There's not a single pump that we have in the industry that could overcome that, right? What we're doing is there's 2 things at play here. One is diameter and one is length. So we want to use both of those to our advantage. What we're trying to do is we want to stay as long as we can in this viscous or laminar flow region. Viscous flow is the fast flow. It's the air, it's flying out of the pump, right? When we hold our hand on the end of that pump, we feel that viscous laminar flow. That's the fast flow. Transitional flow is when we transition from viscous to molecular flow. Molecular flow is the slowest flow. It goes all directions. It doesn't have a direction to it. Where laminar flow is one that's coming out and flying out as fast as it can. So how does it measure up? Well, if we look at these, I just cut some of these away so you guys can actually take a look at this. I think it's just interesting to physically see the difference. I cut a true blue hose, an Appian hose, and a 1/4 inch hose, all in half. These are this is what's called a built-up hose. They call this an evacuation hose, but it's actually a refrigeration hose. It's no different. I'll show you some other problems with this, but it's just a regular built-up hose. It's the same diameter as this blue hose is, except this blue hose is an engineered vacuum hose. It's actually polished inside. It's a double wall reinforced hose. This is our traditional, also built-up hose. Same hose as this, just a smaller, just a 1/4 inch hose. But take a look at the different diameters physically, and get an idea of how much diameter we're talking about here. The problem with a traditional hose, using a traditional refrigerant hose for vacuum, is the low conductance speed. Those hoses outgas, meaning that, have you ever taken a set of rubber hoses, like you get a brand new set of hoses, you smell that rubbery gas smell? Well, that rubber smell is gases. Those are gases. If you can smell it, you've got to remove it. You got to outgas. So that's outgassing. If you're evacuating, that hose is actually outgassing into the system, and that rubber smell has got to be removed. So those hoses actually have to break in. So an Appian hose really won't get to its ultimate vacuum for months until you use it enough, or it sits long enough till the rubber actually cures. Where this hose has no smell to it, it'll pull down very quickly right away. Rough interior surface, high adhesion property. Adhesion means water bonds to it or sticks to it. Refrigerant oil gets the hoses contaminated. They're pinprick. They have high permeation. We'll talk about this a little bit further up. When we talk about flow in a vacuum, there's a practical relationship for air. So our viscous flow ends at 100 times the diameter. So when we're talking about our 1/4 inch hose, our viscous flow ends on 1/4 inch hose at 533 microns. Now you guys tell me all the time I want to pull down to 500 microns. This is why it takes so long with 1/4 inch hose to get down to 500 microns, because the viscous flow ends at 533. We go to 1/4 inch hose is 400. We go to 1/2 inch hose is 200. 3/4 inch hose is 133 microns. At 1 inch hose, 100 microns, and at 1.25 inches, 80. Now, I actually have the patent on that hose, on that blue hose, and I engineered it. And why do you think I stopped at 3/4 inch, just didn't go to 1 inch or 1.25 inch hose?
Not worth the extra.
It's not worth the extra cost, right? When we're picking up between 3/4 and 1 inch hose, we pick up 33 microns, right? But look how much we pick up we pick up 500 or 400 microns with 533 to 133. We pick up 400 microns of work. And I'll show you why that's important in just a minute here. Then this is where molecular flow begins. So molecular flow on 1/4 inch begins at 16 microns, on a 3/4 begins at 5.33. So you can see that we're between 133 and 5.33, we're in that transitional flow, right? But we're staying basically, and the whole time we're doing our evacuation, we're staying in that viscous flow range. All right, why aren't the 1/4 inch ports a factor? Well, we summed it up, Phil summed it up, it's the length of the port. So if we're to calculate down there at the bottom, which is sort of covered up there, but that port is good for about 6 to 9 CFM per port on a 1/4 inch port. All right, overall pumping speed of the system. This is another interesting thing we talk about. There's 3 things in a vacuum that we got to consider. They got the speed of the pump. So that pump is an 8.4 CFM pump. We're connecting it to a connecting manifold, which is this hose, which can conduct 56 CFM. Then we're connecting it to a system. The system also has a conductance speed. So when we're talking about like a residential system, we're using 1/4 inch tubing. Well, that tubing has a lower conductance speed than, let's say, 1.1 inch. So sometimes when we look at evacuating a chiller, like a big vessel, you can actually do it way faster than you might anticipate, because you have very large tube diameters, which have very high conductance speeds, which we can move the gases through very quickly. So if we're to look at this, what we want to have is a ratio of 4 to 1 is desirable. So it means in less than 20% loss. All right. If we look at a true blue hose, a 3/4 inch vacuum hose, our conductance speed here is, we end up with a 12% loss for the hose on the system versus 94% loss with a 1/4 inch hose. So what I'm basically telling you is, you take that pump right there, you're going to lose 94% of the work that it can do when you hook it up to those analog gauges. All right. It's the limiting factors, not just your hoses. This goes where the conductance line. So we had 3/4 inch, 50 foot of 3/4, 50 foot of 3/8, and a 1/4 inch vacuum line and 5 CFM pump. We did the math here. Well, the conductance speed of the system, basically I broke it down here to conductance speed of the first refrigerant line is 3.29 CFM. The 3/8 line is 0.2 CFM. So the total system conductance is 3.49 CFM. The pump, the conductance speed of that hose is 0.2 CFM. So the limiting factor is the hose. The pump can pump 5. So the system conductance is 3.49. The connecting hose of this was 0.2 CFM, and the limiting factor then becomes the hose itself. Over here, I took it to an 1.1 inch line, a 1/2 inch line. So now that goes to that 1/4 inch and a quarter line can do 16.65 CFM. We can do 0.65 CFM. So the total system conductance is 17.3. We're 58 CFM on the hose, 12 CFM on the pumps. Now the limiting factor is the pump, right? That's what we want to do. We don't want to throttle down our system by having the wrong hoses attached to it. So this is another little demo here. I want to show you a couple things here. This is just true blue hose versus standard hose, and this was time to reach 900 microns here, or time, sorry, this was, think of what I was doing here, I can't remember, it's, I was hitting 100 microns on the system here. So and I was just showing the time difference, of what happens with the flow. So gauge one was true blue at 95 microns, the quarter inch hose was still at 1,000, and the Appian was at 500. And this was 15 minutes in. So, and you can see the true blue hose here was down at 500 microns, right, in less than 2.5 minutes at 500 microns. This was the Appian hose, which hit at about 7 minutes, about twice the time. And then I didn't even bother with this quarter inch hose to see when it would hit 500 because we were 15 minutes in and it still hadn't hit yet on there.
What were you attached
Recovery tank.
Yeah.
All
All right,
so how big of a pump do you need? Well, a 2 CFM pump is adequate up to about 5 tons, and a 5 CFM pump adequate up to 10 tons. And here's the interesting thing. For larger units, an 8 to 12 CFM pump will get the job just as fast as a 50 CFM pump. Why is that? We just covered it. What are the 3 limiting factors? One was a pump, one was the hoses, the other one is the system itself. Because the systems we work with, the size of piping works in our industry, doesn't make any sense to go bigger than about a 12 CFM pump, because the system itself, the ports we connect to, the system itself becomes a limiting factor. So the reason for this is the refrigerant lines to be evacuated are so small and so long that they create the resistance to gas flow under high vacuum conditions. Manifold hoses are second, if not many times the first biggest resistance, right? 12 CFM versus a 2 CFM pump. So this was, again, hooked up to the recovery tank. I hooked up just the way you'd normally attach it. 12 CFM pump, 5 micron pull. 2 CFM pump can only pull down to 10 microns. So what I did is I tested the pump first to see how far down the pump would pull down. So how much faster would the bigger pump be? Well, when we do this, initially, this is the bigger pump here. Initially, it has a faster pull down. Why is that? It's a 12 CFM pump, right? So what initially what's the largest resistance to flow in a vacuum? Initially it was the pump. The pump is definitely initial at about 5 minutes there, a little less than maybe 4 minutes there. What transition to be in the larger resistance now? Well, the flow, the hose, right? So you can see right here is that at 7 minutes here, we were at 500 microns. Or with a 12 CFM pump, we didn't hit the same thing till 15, right? That's literally the pump. That's how little the pump has to do with us. It's all the magic is in the hoses. It literally is in the hoses. The hose size really matters. 96 times faster than quarter inch hose, right? All right, before we do this, I want to show you another little demo on here because I just think it's pretty interesting to see. And I'm going to switch the phone over to a different app here for just a minute. And so we can take a look at this. Let's see. And I'm going to flip this around for me so I can get the phone the right direction. And we will swap screens here for a second. All right. I got the right gauge. I have gauge here. I have tons of gauges at my office, so. Oh, maybe I turn on Bluetooth. Okay. All right, so we're going to pull this down. We're just going to see what the pump will do here by itself. And what I'm going to do is I'm going to put this on that graph here. All right. So we'll graph this for just a minute. It's another software app we built.
Yeah, but no, shut up.
Yeah. That'll be more interesting when they open it up. I'm gonna restart it just so we can see the whole graph. Get glasses on so I can see. Restart recording and. All right. So that pump, we'll let that run for a minute. Microns are down at the bottom. Make sure I got all these caps tight. All right. Something's here. Oh, maybe the gas. That pump should pull down and hit. What could be the thing? I might have lost the gasket here. Yeah. There's something right here. Got a clear coupling. Figures I gotta do a vacuum demonstration. I have something to rock. See if the pump's out. Might have been my pen getting blocked a little bit on there. All right, so we're at 25 microns with the pump will pull, right? All right, so let's hook a 1/4 inch hose. All I'm gonna do here is disconnect this gauge and put a 1/4 inch hose in the end. The reason that pump wouldn't pull down is I had that flow valve on the end. If we can't gas out, we can't pull it out, we can't get it in. Like basically the restriction, just the flow gauge was throttling down. All right. We're coming down. What happened right there? We're starting to do what? Let me pull this graph down so we can see this a little bit better. Logarithmic here. You can see initially we pulled down really fast here. We're now at 20 microns. Right before we started to stall. About atmospheric pressure on you see here. About 1,000 microns. That hose started to stall out. Right now we're trying to get down to what? That's only 5 foot of hose too, Mike. That's not 10 foot of hose. That's 5 foot of hose right there. Right. Now it's gonna take us a while to get down. That hose is stalled here at 500 microns. Now that pump can pull 20, right? We're losing all the work the pump can do. So let's go up to this. We'll go up to this nice big Appian hose. Let's see what happens with that. Like looking at a giant rubber snake. All right, so that's nice and snug. Got the big 1/4 inch cap on. All right. We'll pull back down again. You can see it flowing way past with that one. You can still see it. Stop falling out here. We're at what? 300 microns when we start to stall, right? So again, what we want to do is we want to do all the work that the pump can do to the end of the hose, right? So let's here, just so we can see here. Now this hose, by the way, Appian rates this hose at 20 microns. If you ever looked at Appian, That hose will never pull 20 microns. It's absolutely impossible. Just you can't do it. I know how they, it's rated there, but they can't do it. You can see right here, we're gonna pull down much further, we'd have some struggle. So let's go down one more down. All right. So. Wow. I did that a couple seconds there. And that pump, that hose just came out of my car. It's sopping wet. I mean, it's not dried out or anything, you know. It's sitting out here, in here, but you can see now we're down to 73 microns. We're going to let that run for a few minutes. If you look at the angle that's vectoring there, we're still cranking down. We'll get down to under what the pump to do in a few minutes. It'll equalize out, right? So we literally went here from 500 microns, 200 microns to 60 microns down that hose, right? Which basically the pump can only do 25. So right now we lost about half the work the pump can do, but we're still, you know, we'll get down close to what it can do. So you can see how much hose plays factor on each dry evacuation. Now let me show you something else on here. We put back to the PowerPoint. Just fill this. All right. So functions like gas valves. All right. It's not the thing you crank shut with your pliers and leave shut forever. A lot of people understand what the hell that thing is even used for. Well, liquid water destroys the usefulness of vacuum pump oil by increasing the vapor pressure. The pump can't create, if the pump cannot create a vapor pressure higher than that of its sealant, and the oil's a sealant. So the ballast injects air into the second stage of the pump to dry out the condensed water and oil. And it only works from 20,000 microns to about 2,000 microns. Once you're below 2,000 microns, shut your ballast on your pump. Now, in most cases, we're pulling down like with this True Blue hose here, it's down below 20,000 microns before you can blink. It's literally on a standard system, it'll be down below 20,000 in the first 30 seconds back unless it's sopping wet. And I'll show you that in some pictures here. But the gas ballast basically is our first stage, this is our second stage. Again, we talked about that 99% of the load here is moisture, so all this is just water right here. So the ballast, you open it up, it injects a small amount of air in there, and that air is drier. Even at this 80% relative humidity, it's drier than the oil in the pump. And so we inject that air in there, it dries out the oil and drives the moisture out of it. That's all it does. It just allows you to dry your oil out. Here's why this is so important. The moisture is just robs us the time. As the temperature goes down, so does the specific volume increases. So we're to take a teaspoon of water, and this is why we never ever want to evacuate in the winter time. Okay, if we evacuate in winter, it takes forever. A teaspoon of water is 0.0092 pounds, right? It's nothing. At atmosphere at 212 degrees, it's 0.24 cubic feet of water vapor. If we reduce it down to 32 degrees, it goes from 0.24 to 30 cubic feet of water vapor. At 20 degrees, it's 51 cubic foot of water vapor. At 0 degrees, it's 138 cubic feet of water vapor. So with 1/4-inch hose and a fuel piece BP85 pump, it's got a 0.2 CFM now choke down rating. Remove that quarter teaspoon of water would take 11.5 hours. Just a teaspoon of water at 0 degrees would take you 11.5 hours to sublimate, right? With a True Blue hose, you can get it down in about half an hour. Now this is two things here I want to explain to you here. A lot of technicians when they evacuate, right? A lot of technicians when they evacuate, They pull down, they hit 500 microns, they go 500
You're done.
microns, I'm done. Cut the gas and let's go. Well, this system here is soft and wet. As soon as I hit 500, I isolated it, and this is what's called decay. So how do we know that this is decay and not a leak? It's because the line is curved. So, and I'll show you that in another slide here. If the line had a straight up rise over run, it would indicate a leak. This curve indicates moisture. This is a buildup of vapor pressure, so eventually it would peel off probably at about 2,000 microns or so. That'd be the vapor pressure of the water. The first time I pulled it down, hit it. When it hit 1,000, I just isolated it, pulled it back down, hit 500 again. You see it took a longer time now to decay. Pulled it back down again, longer time, pulled it back down again. So this is over an hour and 15 minutes at that point, and we're to get it down to 600 microns, right? So I just playing around with it on there, but you can see that that moisture takes a tremendous amount of time. So how do we evacuate? Well, first of all, you always want to keep your piping clean and capped. It's absolutely critical because the drier we keep the piping when we start, the better it's going to be. We always want to sweep before pressurizing. This is something everybody misses, okay? How many of you guys own an air compressor? What do you have to do frequently with your air compressor? At least once a couple months. Like drain the water out. You take a big system, it's full of atmosphere. You go and you pressurize it with nitrogen, you squeeze all that nitrogen, guess what all the water does? It falls out in your system. Now I have pools of liquid water sitting inside of my piping. Because I take it up to 500 or 600 pounds of pressure, right? Your air compressor home's 125 pounds, 150 pounds tops. Take it up to 600 pounds, all that atmosphere compressed, the moisture falls out. Now we have to take, it's not water vapor we're removing, it's liquid water we're removing. In order to remove liquid water, we got to change it back to a vapor, which takes energy, a lot of energy to do that. All right. So we always want to push all that atmosphere out. That's called a nitrogen sweep. So we pressurize from one side to the other, push all the atmosphere out. Then we pressurize the system with dry nitrogen. We only want to vent it to about 1 psi after a pressure test so moisture cannot enter the system. Start with clean, dry vacuum pump oil. And we always want to perform a single deep evacuation. You do not want to triple evacuate. It's a huge waste of time. We want to pull below the target and hold for a thorough dehydration. So in here, my maximum decay target is 500 microns. I pulled down to 250. Notice this is 4 minutes. This is a 4-ton residential system with probably 100 foot of 3/4, 3/8 line set, 4-ton coil in the line set, right? 4 minutes, hit 250 microns, isolated it off. Notice that there's almost no decay here. This is 20 minutes later, it's still at 239 microns. That's a clean, tight, right evacuation. After it hits the 239, I might bump my vacuum pump on again and just pull that additional moisture out because I want to keep that system running as long as we can. So I want to get all the moisture out of it, right? High vacuum pump oil. Deep vacuum pump oil has to have a vapor pressure of about 5 microns at 100 degrees. So don't buy cheap oil. It's just the moral of the story here. Pull the cores out. A 6 CFM pump with a core in is 0.2 CFM in atmospheric pressure. That's how much the core restricts it down. With the core removed, it's 14 plus CFM, right? It's doing, and I actually it's closer to, with a true blue hose, it'll flow a full 14 CFM, but with a standard core, we're finding about 6 to 8 CFM, but you can see the difference when you pull that core out of there. Use dedicated vacuum hoses, right? Appian so ticked at me, they won't even talk to me anymore because I told them that their hoses didn't work right. And it's because they're pinpricked. Pinpricking in the hose permits trapped gases to escape the hose carcass. You know why it's called a carcass? Because that's dead technology, right? and if you look at that hose closely right there, you'll see that black hose has pinpricks every inch. It has a pinprick in the hose in there, right? And so we want to use a dedicated hose for that, not a charging hose. Obviously, you need to use a vacuum gauge. On your compound gauge, obviously, it usually looks like this where the 0 is not 0. It goes down to 30, which you can't achieve. But you can't tell the difference between 29.14 and 29.96, which is the difference between 20,000 microns and 100 microns. Right? There's no way you can see that on your, it's like trying to measure feet with your car odometer. Right? Vacuum gauges, there's a lot of the vacuum gauges come out in this industry are hiding all the information the gauge has got to show you. This gauge goes 2,000, 1,500, 1,000, 750. It's got huge ranges. You don't see the decay happening. You don't see what's happening in the vacuum. Right now, in fact, if we go to switch to this just for a second here, I'm gonna switch back to my app for just a minute here. We're at this, when we isolated this off, anybody know what happened here? This is not a leak. What is that? What are we seeing right there? That's vapor pressure built back up in the hose. That's moisture, right? That's literally moisture. That's decay, right? So that hose, remember I told you that hose was wet, the vacuum pump's wet, it hasn't really run, it hasn't dried out too much. And that's a very tiny volume of on there, but that is moisture that we're seeing right there. Now, if this was a leak, I'll just get a, if I don't know if I can crack it small enough here.
Leak would go straight up.
Yeah, it'll go pretty much straight. Well, if it's a small leak, it'll go up at a 45-degree angle or so. Yeah, pretty much straight up, right? Well, that's rise over run. That's a good indicator of leak, or within a 45-degree back line, it'd be definitely a leak. And I'll show you a picture of that, what a small leak looks like on the system here. All right, avoid improper attachment. So avoid small diameter hoses, avoid excessive hose length. Look at this here. This guy's got his hooked up their core tool. He's got his vacuum gauge on a 1/4-inch hose, half a mile away from the system, right? This guy's got an inline gauge hooked up on his gauges. That is not where you want to measure vacuum. I don't want to know what the vacuum is at my gauges. I don't want to know what the vacuum is in the far end system. I don't want to know what the vacuum is there. I want to know what the vacuum is on my system itself. So I want to have that gauge right on the side of a core tool where I can isolate it off. I want to use large, short diameter hoses, cores removed, direct connection to the pump, no manifold on there. Use core tools to isolate the system off. Gauge directed to get the gauge connected to the core tool and vacuum rated hoses. The deep vacuum method, this is, again, we pull down, we isolate, flat line, that's a very clean, dry, tight system. Evacuate it at least 2 times allowable decay. So if the manufacturer is at 1,000, we want to pull down to 500 and let it decay to 1,000. If our target's at 500, we want to pull down to 200, 250. Ideally, we exhaust to 100 microns or less. Again, this goes back to 1959. The manufacturer would say get below 100 microns. Right? We literally forgot how to evacuate. The reason manufacturers don't say 100 microns are like, my God, the guys would be there for 7 days because they're using 1/4-inch hoses, right?
Yeah.
The manufacturers have forgot this stuff too. So we're teaching the manufacturers on here. After we isolate that, we want to have a decay rate of at least 1 micron a minute or less. This is 0 microns a second. So this means that decay is pretty much stopped on that system right there. Triple evacuation, this is what is called sweep dilution water method. Notice how long this was supposed to be. So you evacuated for 15 minutes. You broke with nitrogen. You waited an hour. You evacuated again for 15 minutes. You broke. You waited another hour. So how many minutes is this? This is 45 minutes. So 2 hours and 45 minutes. Why do we have to do this? Because the pumps were not 2-stage pumps. They could not achieve a deep vacuum at that point. And so the first 2 pull downs were about 27 inches. We just couldn't get down to that 500 micron level back then. Some of the mini split manufacturers are still prescribing this method. They just don't know any better. But a single dry pull down is the best way to do it, right? Air nitrogen does not hold water. Doesn't happen. The water vapor does not dissolve into or absorb into the air or nitrogen. It simply resides in the empty space between the molecules. So we can use it to push water out, but it doesn't absorb it. It doesn't absorb it. It's not like a sponge going in and sucking it out. When the compressed air is cooled, the water molecules fall out. So this is again why we want to make sure we're sweeping and not pressurizing first. And when the air is heated up, there's more space for the water vapor to carry out and reside. But you can't, again, if you were to think about trying to blow a system out, you can't carry it out. You cannot carry liquid water out with that. It won't blot it up and won't absorb it. Properties of moisture, we have 2 properties called cohesion and adhesion absorption. Basically what we're talking about is adhesion is water vapor sticking to the walls. Cohesion is water vapor sticking to water, water sticking to water. And The process of degassing, the oxygen removal also causes dehydration. Water sticks to water and water sticks to stuff, so it happens on the surfaces. And basically what we're doing is we're breaking those bonds so that everything in this room is covered in water vapor right now. We're just surrounded in water. And it's stuck to the tables and everything else. And that's why, like, when we talk about dehumidification, why it takes so long is because we have to break those bonds of both cohesion and adhesion, and that's called desorption. Basically, we got to supply it with energy to do that. Reducing the pressure is one way of making the water molecules vibrate faster and pop off. So how low should you go? 1959. Finishing pressures of 100 to 200 microns are desirable to make the air in the system so rare that there's only insignificant weight left over for the refrigerant to absorb, thereby establishing good control over the head pressure of the compressor. So comfort cooling is where we recommend a new installation, 100 to 200 microns, so the max decay of 500 microns. Service, you're never going to get down typically below 1,000 microns and holding. Why is that? Especially on 410A systems. As soon as it's open for service, what's it do? Absorbs moisture. And you cannot remove moisture from POE oil with a vacuum pump. It takes forever. So what do we need to do if we can't remove the moisture with evacuation? How do we remove the moisture? Dryers, right? Yeah, desiccants, the only way we can remove it. Ultra low temp. If you're getting on ultra low temp, we need to get down to 50 to 100 microns, decay no more than 200 microns max. Then there's transport refrigeration, right? Can you vaporize or damage the compressor oil? Some people will tell you. In fact, JB has been publishing for years that if you pull a vacuum too deep, you'll evacuate. You'll boil out the oil out of your compressor. No, you cannot do that. It's impossible, right? You know, Copeland regularly pulls down below 100 microns on their compressors. You can pull moisture out. You can pull gas out of oil. You cannot vaporize oil even at 30 microns. The vapor pressure is way too low. We talked about before, mineral oil has a vapor pressure of 5 microns. Mineral oil, just regular mineral oil. You could put PO oil in your vacuum pump and run it. It would pull down as long as it didn't get real wet. You could pull it down quite a deep vacuum with it. But when you see bubbling in the oil, it's just typically removed moisture or refrigerant in there. All right. This is just talking about the gauges and isolating it and watching the rise on there, which I just showed you guys a minute ago on there. But this one's the important slide here, is when you're using a TrueBlue gauge and you're using that app when you have a leak. So this is isolated off. This is a leak. You can see a constant rise over run here, straight up line where this is the tailing off and this is moisture, right? So you can see here the decay rate's 42.7 microns per second. It's a very constant decay. If you watch that, it would stay right around that 42, 43 microns per second. It would just be going straight up. Where this one is tailing off and it's eventually going to stop, it'll stop on the vapor pressure. Notice where it's at again. It's right there around that 3,000 micron mark here. Same place we're at before with this one here. It's just moisture in the system, right? All right, textbook evacuation. This was 6 minutes to 500 microns. Again, I'll show you this other, I think I got the system here, but 17 minutes to 75 microns on a system. So it's not very hard to pull it down quickly. This is a stall due to moisture. So this, when you're pulling down a system and we get this stall here, what's happening here is that it's the saturation temperature above freezing, but the water's boiling off here. So this is what this graph is actually happening. It's water bubbling in a system as we're pulling it down. That's why it's not a laminar flow like that. It's actually water bubbling off. It's continually reducing in temperature. So you can see it's at a 42-degree saturation temperature, which means that water is down to 42 degrees. What happens when it hits 32 degrees? It turns to ice. Once we're at ice, we're in sublimation. It's going to take forever for that to pull out, right? This is a stall due to sublimation. So you look at our saturation temperature right there, 1.7 degrees Fahrenheit. So when we're pulling down, and notice where we're at, that's 1,000 microns. We're a little over 1,000 microns. If you have moisture in a system and you're pulling it down fast, that water will continue to drop in temperature until it turns to ice. Then that ice will continue to drop in temperature because as the ice changes state, we absorb heat from the ice and drop it in temperature. In this case, we're down at a 1.7 degree saturation temperature.
So that's
So
like
ice in the system, this is where it's gonna take
forever.
hours and hours and hours. We have it down there, because the gas is getting colder as it sublimates.
This is an
This is an
interesting
interesting characteristic we see periodically. This is
a
a
partially
partially open
valve.
valve core.
What's
What's
happening there is
the
bubbles.
bubbles.
This is an open valve core. There's this little oil film right here. Every time
gas blows through that,
it creates that frequency on the gauge. And it's just
because the side port of the core tool is not fully open
out there.
on
So you
there.
want to
So we
open
wanna
that up
open
all the way.
way.
This is
Another
another
characteristic that we see
periodically.
periodically.
Notice the difference between, notice how that one's trending. Look at the
Look at
difference between the two trends here. You'll see the different jaggings of the line. This is refrigerant bubbling out of service valves. This is a brand new system. Customer called me up, they're like, I cannot get this son of a gun down. Both these are the same thing, ended up being service valves that we're holding that had a full charge of system in. It's indicated by the upward trend after isolation,
right? Bubbles closer to the gauge will be sharper increases in pressure. So this was, this one here was probably the gauge was on the liquid line and the leak was on the suction. This was the leak was on the liquid line right next to the gauge. So you can move the gauge around sometimes and figure out where things are leaking from. Right? Single hose evacuation or decay test without the pump isolated. If you have service technicians in the field, you want to know if they isolated their pump. Well, I can tell you, they hit a certain micron range there, but they did not isolate it and see if it was doing this. Is evidence of an isolation. So when I pulled it down, I isolated, I get a small rise, and then I get this flat line here. That's a great evacuation. That's a finishing vacuum at 200 microns. That's what it should look like. That's your job documented, well done, right? Exponentially faster. This is a 2,500 ton chiller at University of Kentucky, 30-inch suction elbow, evaporator condenser the length of a school bus. They had, when I went out there with Johnson Controls, they had a 15 CFM Welsh vacuum pump that had 1/4-inch hoses hooked to it. They had a lot of them. They had a lot of 1/4-inch hoses, so it was gonna be really fast, right? They bid 4 to 6 days to evacuate that chiller, 4 to 6 days. We did it with a single 3/4-inch hose in 17 hours. 17 hours, and that was one hose, 12 CFM pump, no oil changes. When it came in the next day, it was 121 microns at the pump and 314 microns at the far side of the system. Anybody know what York calls for on that chiller for micron rating? 1,000. Yes, so if they want 1,000 microns, we're at 121 at the pump. So we probably hit the York requirements probably around 6 to 8 hours, not 17. That's to show you how dry it was when we were done. Residential system, 100-foot, 3/4 to 3/8 existing line set was flushed with R11, 4-ton evaporator coil, 5 minutes to less than 200 microns, right? The reason this is so important is because oxygen and moisture are the enemy. Oxygen is an oxidizer, it turns the oil black. The hydrocarbons can vaporize the motor windings, good acid sludge. Those are our compressors we pulled apart. Those are not copper plated from the factory. That is acid that stripped off the copper, deposited on the bearings. This is why bearings get tight. This is why Supco says, yeah, you need a hard start kit. Yeah, you need a hard start because it's hard to start now because the bearings are seized up because all the copper in there, right? So this is what we're trying to avoid. Oxygen and moisture are the enemy. Formic corrosion. How many of you have been seeing what we think poor quality evaporator coils from China and all this stuff? Copper's definitely getting thinner. There's no question about it. But poor evacuation many times is what's eating the copper from the inside out. That acid's created inside there, it creates formicary corrosion. And for formicary corrosion to take place, we need to have oxygen, water, copper, and organic acid. Guess what? Those are all in a refrigeration system that has moisture in it. It's known as ants nest corrosion that eventually eats through and you end up with all these little microscopic leaks everywhere. You want to avoid that? Just do proper evacuation. All right. So that's all I had. I didn't have any additional notes on here, but one quick note, that gauge will drive you absolutely crazy because it will never sit still. It will always be rising in pressure because it's either rising in pressure from moisture or it's rising in pressure from a leak. But that gauge will not sit still because it's showing you everything that's happening in that system. Everything leaks. What we're concerned about is the rate that it's leaking at. So so that if you look at that, I told you back then, it's a permissible rise of 1 micron per minute. So after that system stabilized, we don't want to see that leak rate going up more than 1 micron a minute. That's telling us that it's very tight. And that 1 micron a minute is moisture breaking off, because we'll never get all the moisture out of a system, but we got it down far enough and it's dry enough that there's not massive amounts of moisture that are liberating from that system, right? I was showing here, I guess you can't see it on that display there, but I was pulling down a two micron gauges. We're at basically 24 microns on the pump and 24 microns on the gauge after a little while there. So it's, but everything leaks, but it's basically, understand that's what's going to happen. All right. So any questions on any of this stuff that I can answer?
Ballpark price of blue back roll.
Oh, the gauge itself?
Yeah.
Less than $300, like right in that range, I think. I don't know, you know, I don't sell any of this stuff, to be
All right.
honest with you.
Just pulse.
So, yeah. But that gauge is a incredible gauge. I know the guy that engineered, they're actually repairable. So they're made in the United States. They hoses are made in the United States. Hoses are made in, actually in Ohio. So,
The blue back hose,
yep.
what cost of that?
I think about, you know, again, I don't know right off the top of my head, Phil, but I want to say the hose, the core tool, and the connectors and stuff like that is a couple $100 or less, about $175. The interesting thing with these blueback hoses, and one of the things we found is that it was sort of a pain sometimes to get a hose. These are really quite supple compared to some of the other hoses out there. They're pretty soft, but these actually, this is what I have a patent on, is the end of the hose. So if you get a hose that you can't get into an area that's really tight, take this little screw off here, and this clamp pops off, and then this hose end can be swapped with this like 90-degree. So if I'm in like on a mini split or something that's tight and I want to pop that on there, just swap the hose end off and clamp it back on. I just got to get the clamp lined up. It's tough if you don't have good sight anymore. So this just goes on there, and this just holds it on. You don't have to clamp this tight. In fact, if you were to take this O-ring off here, this fitting won't allow this to go beyond that, right? There's actually a hard mechanical stop on there. So the O-ring's creating the seal, not the pressure from the clamp. So you don't want to over tighten these clamps. It's just tight enough that it holds it on, and that's all you need to do. These are the same fittings that you see on like industrial vacuum, things like that. If you're looking at industrial vacuum, it's the same type of fitting. When I patented on here, if you know vacuum, this O-ring used to be called a centering ring, was 2 pieces. I designed it into this end of the hose and got a patent on it. So that's it, you know, but it allows you to turn it different directions, get it in where you want it, change the end of it. These come with a half, a quarter, a 3/8, so you can go different size if you got different size equipment you want to work on or whatever you have. So in the gauge, the application, we made the app for the gauge. I brought some copies, by the way. I don't know. I don't know if I gave any of these out, but if you, and you guys have copies for review, do you have a copy of review vacuum service engineers?
No.
So I did bring some copies of it. I republished this, so it's quite a bit of, it's all the original book plus the if you're not going to use it, you're welcome to give it back to me, because it costs about $20 for me to publish these. But if you've been trying to get this back out so people can understand vacuum better, because there's just so much in there. It's a great little read if you want to take the time to do it. And if you notice the back of the book, if you go all the way to the back, you notice that gets sort of colored, and it's in the stuff. That's the new stuff I've written on vacuum, and sort of modernized it with some of the new graphs and things that we have in there. So a lot of good information on that. All right. I don't know what time, 7:05. I think I hit them at the time. All right.
Anybody else have any questions?
If you want to buy any stuff, True Tech Tools is local. They have it all in stock.
Like any of the supply houses, like,
Yeah, there's a few of them that do. I'm not sure who around here, stocks and stuff. You know, I don't get involved in the sales side too much. I know I've seen it at RE Michael and Akron. I've seen, Haybagger. I've seen the hoses and the gauges there. But True Tech's, they're right in Akron, so we usually get stuff in a day from there.
I can
So,
tell you this, that when you order online from True Tech, it does come in a day.
yeah, they ship everything same day. Yeah. They're darn near as fast as Amazon.
Food time?
True Tech, TRUTECH, TrueTechTools.com. All right.
Thank you, Jim.
Yep, no problem.
Got going on there, Jim.
Which part?
That's the vacuum hose. That's
No.
quick.
Oh, yeah.
Small holes.
I've been working on a lot of projects. We did, JB's app. We just did theirs. We did, AccuTools, we did Subcos. So a lot of companies don't want to get in the app development business, so we've been making software for a lot of different companies now. So we've got 10 different manufacturers of probes in the app now. So we've got JB, Testo, Fieldpiece, AccuTools, CPS, bunch of different brands of tools in there now. So.
This all